Hello, everybody. My name's Philip Roth. I work at the Oak Ridge National Laboratory in Tennessee, just a few hours north of here. It's my privilege to welcome you here to SC24. I'm the general chair of this conference, which means I lead the organizing committee, and we've been planning this conference for 3 years. I'm thrilled to be here. I'm thrilled that you're here. This year is turning out to be unexpectedly a monster of a conference. We planned for certain numbers of exhibit space and numbers of attendees, and we are shattering all of those expectations. Just a few stats. The conference started in 1988. One of the things I really like about the conference is we balance a technical program where people can present their research, latest results, maybe state of the practice, best practices in particular areas like how to run a computing center. But also we balance that with a very, very strong exhibit floor, so think trade show. This year the exhibit floor is the largest ever. It grew about 30% from last year. It is almost 500 exhibitors covering almost 200,000 square feet of floor space. And over 25% of those exhibitors are first-time exhibitors. That strong interest on the exhibit floor also translates into strong interest in terms of number of attendees. Last year we had just over 14,000, well, just under 14,300 attendees. As of this morning, the number of registered attendees is 17,050, so 17,000 and change. So about 2,700 more attendees this year than last year. So that's exhibits in the technical program. We do have other parts of the conference, things like student programming or inclusivity programming. They are also very important pillars to what we provide throughout this week. You may have seen on some of the branding that we've put out this tagline that's HPC creates. I chose that tagline because, and it's purposefully vague, it is intended to capture things like all the things that the scientists or engineers create with those big machines or networks that people talk about on the exhibit floor. But it's also intended to be things like this opportunity for we all to get into a room together, create connections between people that maybe don't know each other or don't know each other well, and hopefully take those connections off into the future, and if you're a scientist or a researcher, collaborate on future projects. I also think I chose it because I wanted to emphasize the opportunity to see people's creative side. And so we have a couple of new features this year, like the Art of HPC, which I'm very interested in seeing. It was intended to be a way for people to submit artistic, whether it's something generated by an HPC or AI type machine, or photos of such a thing. I think I was supposed to go forward one slide, and Isaac is not happy with me. So, Art of HPC is one aspect there. Another aspect is the HPC around the world. So you may have seen that in the lobby, the B lobby. Great big display where people can take stickers and say where they're originally from and where they're working now throughout the world. I was very impressed. I expected to see a very, very strong concentration in the United States, North America, given where the conference is located. But when I walk by each day, I see more and more that are coming from all throughout the world. And that's a wonderful thing to see for an international conference. Like I said, the conference started in 1988. It's been offered continuously in November each year. We are the 37th, I think, instance of the conference. So last year we may have seen historical presentations because it was a round number year. This year, not. The Amber Alert for us. So let me leave you with this. Again, just to emphasize, this year is an unprecedented conference in terms of growth from last year. It's a very exciting city to be in. Atlanta has been a wonderful place to be. This is the first time that the conference has ever been in Atlanta. It was supposed to be here in 2020, but you may remember something caused it to be a online conference that year. So we're the first ones that get to experience it in person. The convention center has been a wonderful place for the conference to be. The city's been a wonderful place. We are feeling very welcome to be here, and I hope you feel that way too. So again, thank you for being here. Thank you for helping us tell the story that we want to tell to all of the other people who couldn't make it this year, such that maybe they come next year. Thank you very much. I'm going to turn it over to Melissa Fratkin, who is the SC24 Communications Chair.
Thank you, Phil. Thank you, Phil. Welcome. Wow, we have a full house. This is awesome. Very excited. I will remember to advance the slide so Isaac doesn't get cranky. There we go. So thank you all for being here. And Phil went through all of the stats and speeds and feeds, so I will not do that again. This room will be converted after this event to an interview room, so you'll have space. You'll be able to reserve space for a half hour to an hour at a time, so you can record a podcast or do an interview with someone. And there is a QR code over in the media office, which is the next office that way, 408. And that's also another space where you'll be able to come and sort of hang out and sit on a sofa and talk to people. And we might be a little bit noisier over there than they are in here, but you know, these things happen. We will be there available from 9 to 5. Oh, there's the QR code right there for scheduling. There are also lockers. If you want to leave some things locked outside the media office, you can do that and then come pick them up later. We just ask that you bring back the locks and the keys before you leave town so we can return them to the office. And then tonight at 5, if you're interested, we will have a behind-the-scenes tour of the NOC at SINET, the Network Operations Center. If you'll meet us in front of B408, there's actually a very convenient elevator that goes right down to the convention floor for the exhibits. And we'll get a tour of what technology they're using. As at this point, we are at, I think it's 8.3 terabits per second coming into the convention center. So faster, again, than we've ever been before. Big things are happening. We have all brought you here today to do a little bit of state of the industry on some of the big hot topics that are going on around HPC and supercomputing. So Nidhi Chappell is going to talk about HPC and AI. And then Dr. Helena Liebelt will talk about the state of quantum computing. I hope I'm getting all these names right. I forgot to ask how to pronounce them, but I think I did it right. And then John Vernvik from Eco Data Center is going to talk about sustainability. The bigger our HPC systems get, the more dangerous we get to the environment. But as my boss likes to say, we are both the cause and the solution for global warming. And then on this side of the table, the illustrious folks from the Top 500 and Green 500 will give you their announcements. Interesting things happening there, I'm sure. And then we'll have time for questions after. And then, as Isaac said, there's lunches in the back of the room, so if you didn't grab one beforehand, you're welcome to snag one on the way out. And with that, I'm going to turn it over to Nidhi. Oh, and then if you advance, your next slide will be there.
Perfect. Thank you so much. Good morning, everyone. My name is Nidhi Chappell. I am the head of product for Azure, and I lead all of our HPC and AI. I also happen to have front row seats to all of our OpenAI collaborations for the last 5 years. So I'll spend the next 15 minutes. My slot is 15, so I plan not to go past that, talking a little bit from my lens, how I see HPC and especially AI evolving now. Please do keep in mind that I have a hardware background, so I will focus specifically on the hardware investment, the supercomputing investment. I wouldn't be able to talk a lot about all the algorithm advancements that are happening, not that they're not that important. But I did, so I joined Microsoft 5.5 years ago, and we had just started partnering with a small startup called OpenAI. Not a big deal at that time. It was just one of those pet projects that we decided to go ahead and work with. And over the last 5 years, my team specifically has built 3 large supercomputers for them. Every time we have delivered them, they are the biggest supercomputers, and we continue to deliver more and more. So I figured it'll be helpful to walk this community through some of the learnings that we have discovered as we have gone on this journey. And what what are some of the learnings we have brought back to the community? Okay, so some of the key events and milestones that have happened on the journey. Again, I will not go roll this slide. This is just meant to show that if you look at the history of AI, there's been a lot of big advancements that have happened. But specifically, if you look at the last 5 years, there's been a lot of key discoveries that have been made. A lot of this has been possible because of the transformer-based models that have come up. And specifically, I will talk a lot about our investments that we have made with OpenAI, how we have brought the Gen AI investments, and what we have learned from this. So we'll speak a little bit about how that has been possible and what we have learned through this. But that said, there's been a rich set of investments across the industry, across the ecosystem, that has enabled a lot of other players outside of Microsoft, outside of OpenAI, to really bring in new models, new capabilities to both science and industry. That has been pretty awesome to go see. One of the questions that I generally get is, why now? What triggered this particular moment in time? And how have we gotten to this point? And one of the things I always say is, the scale at which we have invested as an industry, as a company, as a community has been the key to this. So what we have discovered time and time again is to make models that are really close to human proficiency, you need to have scale. Models that are really large, that can run on really large data sets for a long period of time. Again, models that are really large, that can run on large data sets for a long period of time, result in models that are very efficient and very effective. So to bring all this together, you had to have some really large investments in supercomputing. And this is where I say, I have the pleasure of working on this for last 5 years. We've really invested in supercomputers that have delivered almost 10x capability every other year. And even in the last 5 years, we have delivered 3 supercomputers, and we continue to go on that. And that's just the beginning of this investment, right? Across the industry, we see a lot of investment that is happening, both in compute and the data that is now available for these models to be able to train at scale. And that's what is enabling a lot of the investments you are seeing, a lot of the capabilities that are coming up that are being used. As we go forward, I do think this pace of innovation will continue. We do expect that, not only do I expect, I know the roadmap because we're building it, will continue to actually deliver larger and larger compute capabilities, not just monolithic compute capabilities, but distributed across the globe to enable larger and larger models. The models are also shifting quite significantly. As you will see, as probably most of you know, the models are not only becoming bigger, but they are also training on a rich set of data. We started off with images, then they became multimodal and started to train on videos. And all of these require different set of investments in the infrastructure. The infrastructure, and we'll talk a little bit about what we learned on that. But as we continue to see the next few years, we'll continue to stay on this trend of delivering larger and larger compute capabilities that are available to train these new frontier models. But as we train these frontier models, one of the big driver for all of this is to make sure that we can train at a more sustainable rate. So what I mean by sustainable is you do want to have performance, but you want to make sure that you can actually deliver it within a certain cost portfolio, within a certain performance portfolio. And that also becomes very important as you use these trained models to then infer and deliver value around the world. And we'll talk about that a little bit too, as how cost then becomes a big criteria for all of this. One of the things that we have learned as we have gone through this journey is underlying all of this is a key desire to run these models, these supercomputers at scale. And this is where operational excellence has been key to all of this. All of our customers want to make sure that you don't only have supercomputing capabilities at your hand, but you can actually train on these supercomputers. And what I mean by that is, like I was saying, critical to success of a model is having a large set of compute models that can train on really large data sets for a continuous period of time, many months at a time. So we do have training jobs that run for months at a time. And for us to be able to sustain that level of innovation and that level of investment, we need to make sure that our supercomputers are running reliably. Yes, customers do checkpointing, they do retrieve all of that, but at the end of the day, the time to solution is very much dependent on the reliability of the supercomputer. And this is where, over a period of time, we have really worked through our entire software stack down to every thermal bit coming through to make sure that we can deliver reliability for these large systems. Because at the end of the day, if the system is not reliable or you are checkpointing a lot, you're not going to be able to make a lot of progress. And this is where, both for training as well as inference, which I'll talk about in a little bit, the reliability becomes a big parameter, especially for training when you have a single job that is running across thousands of GPUs for a long period of time. You want to make sure that you are managing your mean times between job interrupts. It's not just about MTBF anymore. It is really about the job reliability, making sure that the job is running correctly and running proficiently all the time. And at this level of scale, to run the job successfully for a period of time, you have to make sure that your mean time to repair, like things do break, GPUs are not as reliable as they used to be, you need to make sure that your mean time to repair, you can fix these things as quickly as humanly possible in the data centers worldwide. So we've had a lot of these learnings to make sure that you can not only deliver compute, but you can deliver compute reliably at scale that can perform for compute levels. And at the end of the day, all that matters is delivering performance at scale and delivering it at a cost point for inference. Now, this is where I shift to inference. We talk a lot about training because that's supercomputing. That's something that is very exciting for all of us. But where do we make money in some regards is in inference, right? So everybody is really invested in making sure that these frontier models that we are developing or the industry is developing, we can actually then use these frontier models worldwide to serve for different use cases. Now, one would argue that inference now needs to have different parameters than what training does. So inference for us has to be a global problem. While training can be in a geography, bound to a region, inference, on the other hand, is worldwide. We have inference supercomputers everywhere. And what I mean by inference supercomputers is, I just actually looked back and said, 3 years ago, we actually submitted our first supercomputer into the top 500. We were actually one of the first CSPs to do that. Now, that supercomputer is actually our minimum size that we deploy worldwide for inference. So 3 years ago, what used to be a top 10 supercomputer is now our minimum footprint that we deploy for inference. This is the level of scale that we are investing worldwide. And the reason we are doing that is, for inference specifically, latency matters, especially as the use cases are becoming more interactive, they are becoming more focused on videos. The latency to your compute, the latency to your data actually really matters. So this is where we've been investing in supercomputers all around. As I look through the future on all of this, we see a roadmap that we'll continue to deliver on. I do think the velocity at which we are investing in this will only get accelerated, because we do still see every time a new generation of GPU comes out from NVIDIA, from AMD, we see almost an insatiable need from our customer base to actually take that performance and implement it in their models. So we do think we'll continue to deliver the next generation of GPUs at really large scale every time, every year, every next few years. So, and the pace at which customers are then able to take these supercomputers and apply them to their science, to their investment, has also picked up quite quickly. Like, we used to be in the case of where customers would go, take 6 months to like really hone in their application and then start to apply at scale. Now it's within 6 weeks that customers are training at large scale the moment they get compute capabilities, and they are all publishing on that one or delivering capabilities. So we do see this cycle of customers actually wanting to have the best performance, both for training and for inference, and then wanting to implement that quickly. So I don't see this slowing down anytime soon. Silly plug for us, just so have it. So we actually did invest in the latest generation of our H200s. We actually will be announcing our next generations of Grace Blackwell 200s tomorrow as well. But as you see through all of these, whether it's AMD GPUs, whether it's NVIDIA GPUs, I really do think for the next few years, we'll continue to see the pace of investment pick up across all of this, and a lot of the learnings from all of these helping us build supercomputers that are reliable, performant, and globally available everywhere. So with that, I do actually think that AI is going to rely on supercomputing more and more so, and we are excited to be part of that community. I think I almost did fine, right, Mine? Perfect. Awesome. Thank you. With that, I pass it off to Helena.
So, all right. Let me see how I can manage with that. All right. So I'm Helena Liebelt. I'm a professor of computer science at a technical university in Deggendorf in Germany. I'm also the technical program manager for quantum computing in Intel, managing the efforts in EMEA. And as the founder of the Institute of Future Technologies, I'm focusing on HPC, AI, and mostly on quantum computing. All right. So, it's a pleasure to be here at Supercomputing 24 to discuss the state of quantum computing. It's an industry with over 9 billion in commercial worth by end of the decade, so it's quite a number. It also is supposed to change a lot of industries, a lot of things along the way. But while the quantum computing is promising a lot of problem-solving capabilities, it is also essential to approach it with a very grounded perspective. So with that, I would say let us have a look at the good, the bad, and the ugly of the recent developments. All right, so first of all, let's have a quick history lesson. When we talk about quantum, everybody is focusing more on the recent development, but we forget that we have that development for quite some while, and it parallels in a way the development of the classical compute, right? So from the time of Charles Babbage and Ada Lovelace, it took us about, as humanity, it took us about 100 years to the first digital programmable computers of the 1940s, right? Same happens kind of with the quantum computing. We are seeing here Dirac with the quantum theory in 1929, and then again the actual statement of how to use the theory in a practical way in the 1980s, largely to the work of Richard Feynman and David Deutsch, right? And I think by the time Google announced the quantum supremacy, it was kind of obvious what the advantages of quantum computing could be. It offers exponential speed up, it offers benefits in simulations, it also is quite great for cryptography and other things. It has unique ability to simulate quantum systems efficiently, so it can accelerate breakthroughs for medical, for material science and other things. So today the governments are investing heavily in quantum computing, and despite that, we still need to have a look at how this is actually progressing over time. So let us have a look first at the good things that are happening. So, as with classical compute during the 1940s and in that time frame, we have a simultaneous development in quantum technologies. It can be spin qubits, it can be photonics, trapped ions, and just to name a few of the major ones. And when we look at the actual direction, we can say that the recent development actually shows that the manufacturers are focusing more on the fault tolerance and coherence, more than the just sheer qubit size, qubit number. Right? So this is more of recent development. Significant milestones achieved in error mitigation and correction are, for example, demonstrated by Alice and Bob, by Amazon, IBM, Microsoft as well. And they also all promise the large-scale, fault-tolerant quantum computing. We have a recent development. I think the announcement came just a few days back from Quantinuum. So they recently announced the accelerated hardware speedup, right? So the new roadmap is actually aiming on delivering fully fault-tolerant and universal quantum computing by end of the decade. So this is new, and I think this is quite awesome. IBM, for instance, also announced the development of the 1,000-qubit modular system by 2026. All right, and Google announced the 1 million qubit version by 2029, which also seeks practical error-corrected systems. The diverse qubit technologies, such as photonic, by psi-quantum, trapped ions by IonQ, neutral atoms by cold quanta, and so on. So they offer each of them unique advantages. For example, the reduced cooling, right? So this is also plays into all those ideal developments. So let's next have a look at the financial aspects. So this is the funding map, and this is just a reduced funding map, to be exact. So we had investments in the past announced, for example, by China with 15 billion, right? We knew about that. We had the quantum flagship in European Union with a couple of billion. Now what is happening is we have the second wave of investments by new governments joining the party. So we have, for example, Australia with about 60 million. We have also Germany, who are adding additional couple of billions to the already announced investments from the past. So we are now over 5 billion in just that space. The United Kingdom is also announcing the national initiative in the quantum space. So all of that is happening simultaneously. What I also want to add is the actual development in the startup market. I think this is also quite interesting. So we've all seen the drop in general for the startups, right? We are at about, I think, 38%, which is quite huge, but easy to explain with the geopolitical developments right now, with the state of the capital market and so on. But we still have to remember that the quantum startup market only dropped by about 27%. So it's still about 280 million, right? But it's less than the overall startup reduction. All right. So in total, the funding, if we look at that, is over the 40 billion mark, which is unique and new. And I think the development is still continuing. So we are at the second wave of all of that. All right. Before we move forward, I think for the good part, we also need to mention the quantum and AI in the same sentence. I think you will see a lot of that on the show floor. If you haven't been downstairs yet, I highly recommend that. What we need to consider in that is that quantum computing has, in general, a significant potential in advancing all of that. We still need to remember the quantum algorithm development, so the QML as such, which is just at the beginning but has a huge potential. All right, so let us go to the bad part. And the most important thing of that is, I think, on this slide. When we talk about quantum computing, everybody, I think, is focusing on the quantum chip, right? So the QPU is on the forefront and everybody's talking about. What we tend to kind of forget or not talk about much is the control electronics. So the miniaturizing, the integration, all of that still needs to happen. We also need to think about the compilers and the runtimes. And we also need to think about the actual application algorithms. So all of those levels need to be addressed independently. And this is a huge area that is being targeted right now. So we have wonderful examples on how this has been managed in the past. So we have, for example, the Munich Quantum Valley, who are addressing all of that. We have Intel addressing the full stack from the bottom to the top in that direction. The good part, though, is we already have done that in the past. So in the last 80 years, we've already done that. We know how to do it, right? So if you look, this is actually one of my favorite slides. If you look from the left to the right, the picture on the far left, this is how computers used to look like, right? And close to that, you have the more modern supercomputer. So look at the quantum computing. You also see a lot of cables, you see a lot of electronics, but just imagine if we are a bit, patient with our development and ambitious with our development, we still have a lot to go, and I'm very confident we will get there. Now to the ugly part. So first of all, I think it's quite obvious that we need to talk about the overinflated expectations, right? And I'm probably not going to make many friends with that, but this needs to be mentioned. So we have, we have the media hype that evolves around that. So everybody is expecting to have those quantum computers ready and being capable to be used right away, which is unfortunately not the case just right now. We're at the beginning of that, but we realistically have a couple of years ahead of us, right? So in my opinion, we need to focus on rather the incremental development that we are doing great today than the lofty announcements that happened, unfortunately, in the past or quite often. The other part is the skilled labor. I just showed you the multiple levels that needs to be addressed for quantum computers to make them available, right, and ready usable. Unfortunately, somebody has to do it. And we simply don't have the manpower and the hands and the hats to do so. So in the past year, we have had about 360-something students graduating in the STEM fields, which are adjacent to quantum computing. But this is still a drop in the bucket, right? So we have an increase in general universities offering courses in quantum computing as overall. We have an increase of 10% for the master's programs. So I, for example, have founded Germany's first master program on HPC and quantum computing. But I only have 2 hands and 24 hours a day. So there is just so much you can do. So we need to expand that, but we also need to expand the collaboration between the countries with all the funding. So all those countries, all those research facilities are not tasked with reinventing the wheel all the time, but actually advancing all of quantum computing, all of the industry, potentially, hopefully, together. with that, I think I'm nearing my 15 minutes. So in closing, I think it is quite realistic that we have already made some progress in that, with about 100 years behind us in all the development. But the traction is there, and we are now addressing all of those levels I mentioned previously, and we are all on a very good way. And with that, I thank you very much for your patience, and look forward to the discussions in the next days. Thank you. Sean is the next one.
All right, hi everyone. Glad to be here. Short introduction to myself. John Wernvik, I'm Chief Sustainability and Marketing Officer at Eco Data Center. We're a data center platform based in Sweden. So I traveled quite a far way out yesterday, from the cold to the warm, as we say. We're a data center company that was started operations in 2019. We're fully optimized for HPC and AI workloads. And now what we are seeing, as Nidhi was saying, we're seeing an extreme amount of pickup for AI compute. So the sense of this talk will be a lot around the sustainability challenges and the challenges to deliver that kind of scale that Nidhi and her team needs to have in order to take these kind of models to the next level. We partner with the likes of University of York and then new clients as well as CoreWeave, the AI hyperscaler. We will deliver. We're setting up 10,000 H200 GPU cluster for them in like 40 days time. So at that amount of time and scale that they are looking for to deploy compute right now is fairly incredible, actually. I'm not going to jump in certain technical issues. We come from an infrastructure perspective, so we like to talk about grid connections, sustainability in terms of energy uses, our connections with communities and societies overall in order to enable that kind of scale. But the amounts of ask we are getting at this moment in time and the exponential growth in that, it will put a tremendous stress on countries and grid utility systems all around the world to deliver that kind of next phase in the computational journey that is now that we see now is happening. A true stumbling block, both becoming that enabler and problem, as previously heard, is of course the increased densities in computing racks that is now going to happen. Of course, liquid cooling coming into place will enable a lot of more sustainability practices, and in terms of efficiency, of course, that is hugely beneficial. But it will also put a huge stress on getting new capacity online. A lot of data centers worldwide can't accept liquid cooling as of right now. We've heard that the adaptation phase is close to like 5%. So the amount of capital and the amount of new build in the data center system for the next couple of years will be immense. I think Jensen from NVIDIA is talking of something like $3 trillion of new infrastructure being put in place. So the amount of numbers going on right now is quite insane. And I know OpenAI was talking about developing a campus of 5 gigawatts of capacity. I mean, and that type of energy demand and where they source that energy and only getting grid access for that type of power will put a tremendous stress on the full society and that full circle of society. So I think we as an industry will need to move pretty fast from not thinking of efficiency in a linear level, but more think about efficiency more from a broader aspect for society as a whole in order to enable these new kinds of compute clusters going on. So we need to adopt a much more broader approach in order to have these kinds of next level compute. So this is a largely societal shift, and we don't see it only in Sweden, we see it pretty much across the board right now, which will be a huge challenge to deliver that scale and that kind of time frame that is now actually being adopted. So some examples that we see about that current adoption rate is that the power shortage, given the general trend of the electrification within society, like 40% of the new build in data centers are affected because of grid access. There's not enough power to actually power these kinds of new data centers. And of course, with as the market supply and demand factors are, electricity prices are going up pretty much all across the board, which is also affecting research. We see that a lot in the UK, for instance, where a lot of universities can't afford the power prices to actually do compute. So then it becomes a much broader issue as well. If you can't get the power into the racks, it will be impossible to do compute as well. So that will absolutely be a major, that is a change that industry really needs to be adopted. And also what we see is that nobody really knows what we are actually doing within this industry. The community has been pretty bad in talking in a broader sense as well. That's why we see a lot of community pushback pretty much all around the world, which is also a hampering effect to deliver that kind of next generation scale that we need as an industry as well. So now there's a lot of good things going on, engaging with community and being more transparent going forward. So I think that will be a major change that will need to happen as well. We're seeing a lot of data center pushback in Virginia, for instance. We see it in Amsterdam, where there's a data center. You can't build a data center anymore. In Ireland, the electricity consumption is 20% for data centers, and for housing, it's 14%. So I mean, it's a pretty. The amount of scale needed going forward will, of course, further increase these pretty crazy numbers going on. And when we actually see what kind of information that is being provided to the public in terms of transparency, it's pretty much only from a linear efficiency perspective. Like power usage efficiency has been pretty widely adopted overall, and that's pretty much the only metric much being tracked and reported. As Uptime Institute said, that PUE is pretty much the only metric that is measured. 75% of the respondents said that. A lot fewer are measuring water, how the consumption of water, etc. Their scope 1, 2, 3s is extremely low. So this will, of course, affect the industry as a whole as well. But of course, there are a lot of good things going on as well. I don't need to be fully pessimistic. There are, of course, a lot of new energy sources being adopted. Of course, a lot of the hyperscalers are looking into nuclear as well, but a lot of the hyperscalers are actually among the top 10 in the world of purchasing renewable energy. So I mean, everybody is looking at their energy consumption because they see that this will be a fundamental part in our sustainability journey as well. But one thing that we see that we really need to look more on is also the sources of backup power. There's a lot of diesel being burned in backup generator at this moment in time, and I think there's a lot of R&D going on, seeing how can we change that either with hydrogen fuel cells or vegetable fuels as HVO. That can have a dramatic lowdown on the CO2 emissions as well, in order to also be reliant, because I mean we can't not build compute not having a redundant system, as Nidhi also said. We need that reliance as well, and backup generators will always be a part of data center design. But can we change the fuel going into them or the different models? That will be huge, and a lot of players are looking at that at this moment in time. We also see new construction materials. There's a lot of adoption now of cross-laminated timber all across the board. Microsoft did an announcement like 2 or 3 weeks ago, which takes down the CO2 embedded emissions something like ×3. So that will also be a huge enabler for the industries to cut down CO2 emissions as well. We say pretty cocky from our end, if I put the marketing hat on, that we congratulate Microsoft joining a club we started in 2019, building in cross-laminated timber. But what we see has probably has the most potential from a energy perspective and having that kind of holistic perspective is actually doing something with the heat generated from the servers. Now with liquid cooling, the temperatures will rise, and we'll have a lot of very cool adaptations going on. There's a lot of things happening in that area. We have Deep Green from the UK recycling the heat to public swimming pools, because a lot of the public swimming pools can't afford be upper the heating with the current energy prices in the UK, and that's a fantastic adoption, which of course makes it a lot easier for society to also accept that kind of data center. So you get a very positive loop, and that has huge benefits, also enabling that kind of next generation scale for compute. And we also see this with a lot of heating houses with district heating, piping, especially in the Nordics. You have some great examples in Canada as well. But that will, of course, also enable policymakers, etc., enforce and happily adapt data centers, because you get exponential effect of the energy use within them. So this is something we really think is going to be adopted within the next coming years, given the scale that will take as well. And yeah, and pretty much all I'm gonna leave you with, I think we need to do more in terms of thinking in a broader sense of what we do, and see what kind of stakeholders do we actually engage with, because we see a lot of good things happening right now, especially within the hyperscalers and some other players as well, all actively engaging with communities as well, because that will be an enabler for this industry to scale further. Thank you.
Well, good afternoon. Let me quickly introduce ourselves. I'm Eric Strohmeyer. I'm here for the top 500. I'm going to give a brief overview of the new list, which is coming online just right now. And next to me, of course, is Czech Tongera, who has been with me on the top 500 from the very beginning, and he's responsible for all the benchmarks we are tracking these days. And to my left, who is Wu, who is going to talk about John Wu. His specialty is power efficiency, energy efficiency of computing, and he's going to talk quickly about the Green 500, which also is the data of which is collected and published under the umbrella of the top 500. So without further ado, that's the new top 10 in the top 500. And of course, we have a new number 1. That's the El Capitan system at the Lawrence Livermore National Labs. It's very nice. It was in the making for a while. It's very nice to see. It was fully measured. It was fully installed and measured at 1.7 petaflops, 1.742 petaflops, the new number 1. Here's a quick slide about it. And if you recognize that one person sitting in the audience, Bronis, he is here to answer any specific questions you have about that system. He's in the audience. So El Capitan is based on AMD chiplets. The chiplets contain 4 CPUs as well as 4 MI300A accelerators together with 512 HBM3 gigabyte memory HBM3 on the node. That's a single node. The whole system has just over 11,000 nodes and has a peak. Each node has a peak performance of about 250 double precision 64-bit floating point operations, 250. That is a peak performance which is a little differently labeled or calculated than some other companies might do it. That is actually peak performance you can achieve if you run DGEM on all of the CPUs and GPUs, so it is an achievable peak performance, not a theoretical one. This is not you're not limited by thermal throttling. You can actually achieve the 250. The measured power consumption during the HPL run, which we published in the Green 500, was 28.9 megawatt. The nameplate performance, electrical performance, is actually 34.8 megawatt. And there are some further details, and as I said, Brownis is here to answer all the specific questions, and we're going to hear more about that in our BOF session tomorrow. So what else happened in the top 500, in the top 10? Yellow are all the changes. So the number 2 system, the Frontier system, which used to be number 1 system, first exascale system ever, they submitted a slightly updated measurement. That's why their measured values are the same, but the system itself actually did not change. Aurora didn't get around to remeasuring their system, so we're waiting for new numbers for that system. It's listed with the same number as in June when it entered the list. There is a new system on, yes, there is a new system at number 5 called HPC6 system in Italy. It's actually one of 2 systems in the top 10 right now which are in Italy, which is kind of unusual because we often heard the question in the past, where is Italy in the top 500? Now Italy is very much on top in terms of European systems in the top 500. It's installed, not installed by the HPC consortium as the other big European systems, but actually by I believe it's a non-profit corporation, NESPA. Okay, this didn't quite work, expected. And so that's a very nice system. One change, which was just a remeasuring of an existing system, was the ALP system in Switzerland, which is one of the Euro HPC systems. Is it? It's coming. No, it's not. It's not. It's no. I'm sorry. It's not a Euro HPC system. It's very much not a Euro HPC system. It's a Swiss system, CSCS. And they actually upgraded the system as well. So the number of nodes cores changed substantially, which allowed them to leapfrog the HPC, Euro HPC system Lumi. So now the Swiss system is ahead of the Euro HPC system first. 2 Euro HPC systems, number 8, number 9. And number 10, another system at Lawrence Livermore National Labs, which is actually a smaller sister system to El Capitan. It's identical architecture, just much smaller. Livermore has 3 systems with the same architecture. RC Adams is the 3rd one. Didn't make the top 10, but the smaller system is actually still large enough to make the top 10. So that's the top 10 of the top 500 itself. Nice change in terms of turnover and things like that, which we haven't always seen lately. If you look at the top 10 systems according to the HPC-G benchmark, which Czech created a couple of years back, you actually see no yellow there because there are no changes. Or to be more precise, there is one change you can't see because Summit was decommissioned last Friday, and by our very strict rules we said we're going to have to remove it from the list. So it's no longer there. Summit otherwise would have been on that list, which of course historically is a very important system. Otherwise, no changes to HPC-G because partially because El Capitan didn't get around to measure it yet, and we didn't get any upgrades for the big systems submitted either. The 3rd benchmark we are nowadays tracking is the HPL Mixed Precision Benchmarks, MXP benchmark, where we measure the equivalent performance if you're on a mixed precision algorithm for solving the HPL problem. And you see we had a few remeasurements for the number 1 and 2 system, Aurora and Frontier. Both remeasured. Their ordering actually didn't change. So Frontier didn't manage to get ahead of Aurora because Aurora also remeasured and increased their value enough so that wouldn't happen. Other than that, very little activity on that benchmark, partially again because El Capitan and those new systems have not submitted numbers yet. So that, and with that, I'm actually going to turn it over for a couple of minutes.
Thank you, Eric. So this is the top 10 of the most energy efficient supercomputers on the Green 500. I guess I'd preface this by noting that I think that as you've already seen from the previous talks, greenness is of increasing importance with the rise of the AI, and the hyperscalers, and the mention from the Eco Data Center talk that the hyperscalers are now resorting to nuclear energy, cleaner energy towards a decarbonized footprint. So Amazon, Google, and Microsoft have all signed recent nuclear energy deals to power their data centers. With that being said, I think what we can see here is that there are 5 new entries in the Green 500 at 2, 3, 5, 6, and 10. I think what's important to note is that they're all well over the 20. They're well over the exaflop in a 20 megawatt power envelope. That's the goal. The goal of exascale in 20 megawatts was translates to 50 gigaflops per watt, and you can see that all of the systems here are well above 50 gigaflops per watt. So it's very energy efficient supercomputers. The other thing you should note is that while the list has a predominant number of supercomputers that are still homogeneous, if you look at the top, about the top 75, the first 75 supercomputers are now all heterogeneous, and they have some form of an accelerator, as you can see in the top 10. We were slated to the target. The DARPA exascale study was exascale in 20 megawatts, which translates to 50 gigaflops per watt, and that was in 2015. It then got pushed out to 2019, and then you can animate again. We finally reached it with Frontier in 2022. So we needed another 7 years of runway to achieve that, but it has been achieved. And this just gives you a perspective on how the list has evolved. It used to be way back. I cut it off at 2014. Otherwise, it's not even readable before that. But it was predominantly homogeneous supercomputers, and what we've seen over the past decade is this massive shift to homogeneous supercomputing systems, which are the ones that are. I'm sorry, a massive shift to heterogeneous supercomputing systems, which is shown in the orange. The orange is it's a box plot, box whisker plot that shows that the heterogeneous supercomputers are significantly more energy efficient than the homogeneous ones. The homogeneous outlier that you might see, that little dot above the yellow, which is the homogeneous ones, that should be Fugaku. So, all right. With that, I think we'll move on to the last one.
So as last table here, I'm going to show you the systems, new systems in the top 500 outside of the top 10. So basically showing what else happens new in the list. And you see the first 2 systems I marked. There are identical systems installed at SoftBank. SoftBank decided to submit them separately and even measure them separately. That's why they have different LIMPAC. Otherwise, they are identical. And together, that system would have been number 11. So those big integrators, they are certainly in the list, and they're showing up in good numbers there. The third system I marked, it's a Euro HPC system now. That one I marked because it's the pathfinder for the first European exascale system. So that is coming online, and that's the first nodes, I believe, of that system. All of those systems, the 10 next system on the list, 9 of those actually are based on NVIDIA GPUs, as you see, and 1 of them on the AMD Instinct, like the current leaders in the system. So it's overall very nice turnover. We only get down to position 32 with those 10 new systems. That's quite a bit of turnover in the high ranks of the top 500, which we haven't seen for a while, which goes hand in hand with architectural changes. So how has performance overall changed? We have been showing this for a couple of years. We have seen inflection points in the growth of performance, first in 2008, then in 2013, 13 for the average system size at the high end. And since June 2017, we see another slowdown in performance growth at the bottom of the list, which hasn't manifested at the top yet. But those trends are very consistent, very stable, even on exponential scales. And if we take the last trend since 2017 and just project out naively from 2017 what performance is supposed to be by the end of the decade, by 2030, we see the blue line for the number one system is barely going to get up to 10 exaflops in double precision. So that's where the HPC community is going. Growth rates have dramatically slowed down, and we have to see how that continues. If it stays that lower, it goes even lower. So with that, I'm going to show briefly 4 slides with more traditional statistics about where these systems are installed and where they're produced and things like that. So you see two pie charts every time, and you're only going to see statistics about the new systems in the last 6 months. So there's 96 systems in the last 12 months, sorry, 2 lists. In the last 12 months, there are 96 new systems, and these are statistics about those new systems. So you don't get the statistics about the old system, just about the new ones. And you see a lot of installations in the United States, followed by a variety of European and Asian countries. The one country noticeable absent for a while now is China. No installations, not because they don't install, but because they don't give us numbers anymore or installations anymore for a while. If you rank it by performance, the right slice pie chart is always ranked by performance, rated or weighted by performance. You see overproportional number of overproportional amount of performance installed in the United States. That's the 3 new exascale systems, or more precisely Aurora and El Capitan. Frontier was on the list before. And Italy is now actually the 2nd largest country in terms of installed performance because of the big systems in the top 10. I think that's the first time Italy is that high, followed by Switzerland. I'm sorry, not Euro HPC, and then the big Asian countries now, of course, being Japan, but also Taiwan. Taiwan has installed bigger systems than they have in the past, and they move up in the list quite a bit. If we look at where these systems are actually produced, we see in terms of geographic, a lot of the systems are actually produced still in the US, with the dominant producer by system count and especially by performance, because 2 of the 3 exascale systems are produced by HPE, is HPE, followed by NVIDIA itself. NVIDIA chips with mostly with the Grace Hopper superchip. Dell installs a fair number of systems, smaller so on the right pie chart they don't show up nearly as much. In terms of other companies, Lenovo is still submitting numbers, but those are installations outside of Japan, so they tend to be smaller. And of course, in terms of European countries, Eviden is showing up in both slices, and once Jülich comes online, we expect that Eviden slice, especially in the right pie chart, to become much larger. What are the chips and the GPUs, CPUs and GPUs used in those systems? Lately, AMD has been installing a lot of systems, a lot of systems with AMD CPUs, and especially by performance, driven by the big systems in the top 5, followed by Intel and NVIDIA. NVIDIA as a CPU is here the NVIDIA Grace Hopper chips. And if we focus on the GPUs only, the trend is similar, except the number of systems with AMD GPUs is much smaller because they are predominantly installed at research installations and not so much at commercial installations. While in terms of performance, of course, the big systems propel that blue slice up very nicely. So that's a brief summary of the big news. Of course, El Capitan is one of the big news, and the technological changes which we continue to see in the top 500. So that was all I had prepared for today. If you want to hear more, tomorrow is our BOF session at 5 o'clock as traditional. And on Wednesday, we're going to have the Green 500 BOF session at 5 p.m. Okay, thank you very much.
Questions for any of this?
My question's for Helena. I'm Heather West from IDC. I'm a research manager, and I lead our quantum computing research. I had a few questions, but I'll start with one, give other people a chance. So you noted specifically about the quantum hardware vendors that are focusing in on fault tolerance. And specifically, you pointed out Quantinuum and their goal to establish a fault-tolerant quantum system by the end of the decade. And I was curious why you chose to point out Quantinuum specifically, since IBM was the first one to note that on their roadmap. It was followed soon up by Microsoft, and then after that, if you look at the rest of the roadmaps that have come about, even though the detail might vary, every single vendor has now shifted their roadmaps to almost mirror one another after IBM did it. So I was curious as to why you picked out Quantinuum.
Great question. Thank you very much. So yes, IBM is the obvious one, and I think this is quite known, right? What I wanted to point out is that other companies are also kind of gaining traction, right? So I mentioned quite a few of them. And for Quantinuum, that was quite interesting, the announcement that they want to do the, let's say, large-scale deployment by end of the decade, right? We also have IQM, for example. They deployed, I think, about 30 systems already and are aiming to democratize kind of the market and make everything cheaper, right? So more affordable. So there are more companies, no longer startups, right? Even though some still call them like that. So there is much more movement in the market.
Other questions? Nope.
I'll do a quick one. On your time series of the Green 500, I noticed that there was one thing, if you could explain to me, I'm trying to noodle it through. It was the bottom has been flat for like the last decade.
Yes.
Can you give a notional sense of why that is, what happened, and what drove that?
So that's the energy efficiency of the lowest part of the list. And so what we're seeing over the past 2 decades is that the energy efficiency gains at the top end have been doubling every 2 years. And then as we go down and you start to look at the median, the rate at which it's improving is not as much. And then of course, as you noted, it's pretty much flat. I think it's not that it's maybe another one before that. Yeah, this one here. Yeah. It just flattens out. Yeah.
Is it just
Yeah.
because not being cost efficient to try to be more energy efficient?
I hesitate to make any conjecture on that, but I mean that is something that stands out. It's the focus of the list has of course been on the high end, but we generally see that as you go farther down the list, the improvements in the flops per watt are much more modest.
It might actually, we would have to look very carefully in the list, because if you look at the minimum, if there is one system in there which is very old, but is on the list for a long time, that might actually keep the minimum artificially down. Right? You would need to look at the minimum of new systems to get the real trend.
I have a question for John. I'm Shaheen Khan with OrionX. So I have just caught up with the complexities of power transmission, and with like Los Alamos having difficulty, physical, political, environmental, all of that. Now do I need to worry about heat transmission too? Because if I'm going to place my data center right next to the nuclear power reactor because that's better for me, how am I then going to transmit the heat to swimming pools?
Yeah, I mean, thinking of heat reuse, I would say that is one example of thinking from a more systematic or holistic approach. Placing data centers right next to nuclear reactors is, of course, also a systematic approach of taking out other parts of the equation affecting communities as well. That nuclear reactor will probably have a lot abundance of more power than to power your data center, which could then be used to the communities close by. So I think it's more of a thing of not cannibalizing on society infrastructure rather than adding. Yeah, it's super. I mean, yeah. I mean, it's we know that there's a lot going on in that space as well. There's a lot of big players looking at it as well. There's a great report on heat reuse from Danfoss, an engineering company that has calculated the exact amount of energy that's being just lost because we don't reuse it. So yeah, I'll make sure to send it to you.
I think he wanted to say something.
A bit of a tongue-in-cheek answer to this. There have been facilities that, in dealing with the heat, that they're, instead of just exhausting it out, they're actually piping it into greenhouses and reusing heat in greenhouses. So, the most recent one that I'm aware of was done at Notre Dame. So, right.
Yeah, you have a few very good examples of that in Canada as well. I mean, I would say that's one of the most favorable adaptation of heat reuse as well, because you also increase the self-sufficiency within the food system in very cold regions across the globe. So that's a perfect adaptation to solve the whole community puzzle as well.
Hi, so my question is probably for Nidhi or for the general panel. So it's great that we're adding so much compute resources. What I also wanted to know was, are there any concerted efforts to, on the user side, to educate them on their job efficiency and optimization so that they can better utilize the resources and not always think about, oh, I want the latest and the greatest, without thinking what's happening on their compute?
Very good question. Just a couple of thoughts on that. Again, I think this is where a little bit of the cost comes into the play, which is cost is a very good driver of realizing at some point there is a ceiling to how much you can afford or anybody can afford. And how do you more efficiently use what you have at hand, right? So our end customers, the data scientists, don't necessarily have incentive to optimize their algorithms, but then pretty quickly when cost comes into play, they are actually starting to look at their overall utilization, looking at what they can reuse, and actually going back and seeing, can you retrofit your models into older GPUs that can actually provide you the same benefit, especially for inference, but at a much lower cost point. So I think some of this is coming naturally from being driven by the cost side of things.
If I may, add a little bit on that. So coming from quantum, for example, the predominant workforce comes from physics, right? So most people are physicists. And well, the physicists in the room may not agree to that, but the physicists, if you ask them if they can do something, they will probably say yes, right? Because they can do everything. But they are probably not ideally educated to do software or some other tasks, right? So what we need to do as society is, there are two things. One is the education, and the second one, what we can also do is upskilling. And this is, I mentioned before, we have many graduates specifically in STEM fields, right? But they focus mostly on different aspects of that. And what we need is a mixture of the capabilities of tools, and there are not many that are equipped to deal with that specific area, and we need to focus on that a little bit more.
Yeah, and I think like empowering the research computing teams at universities and institutes that directly in contact with or in touch with supercomputing data would be great, because right now there is that disconnect, there's a gap, and looking for ideas that can help.
Let me just point out that we have very powerful supercomputers today, and the list that we have here shows the very powerful ones. But LINPACK is something that we measure the performance on, and LINPACK was something that perhaps its time has passed in terms of a useful benchmark. We have another benchmark, which is highlighted here, called HPCG, which is doing a problem which is more relevant to simulations that are done today on our high-performance machines. And if you take a look at the last column, the second to last column, that's showing the percent of peak performance that we're getting on this benchmark. So here's a benchmark that's very realistic in terms of what's done on supercomputers, and our machines are getting In some cases, less than 1%. 1% of theoretical peak. So that shows that there's a lot of room there for improvement, and that improvement perhaps can be obtained by innovations done at the algorithm level and the software level. So there's plenty of room at the top to drive into that performance, and we're really not doing a very good job today, I'll say, of tapping into that. So that, I think, is something we should be looking at and focusing on.
As I say, to address, you worry about the disconnect between the user and the data center, essentially. And so I think a very disruptive way to address it and educate the users is, instead of allocating compute time on the hyperscalers or in the data center, in the supercomputer center, based on CPU hours, you have some type of allocation that is basically done on carbon credits or energy. So that forces the user at that point to say, all right, well, my quota is this much energy, and so I have to learn more about my code in terms of how I use the computing resource.
Well, I mean, we already have that, but despite that, we can see that the labs who max out those tokens are not even in the 50% efficiency mark. They are all within 2 to 15% because they're not realizing how efficiently use the cores or GPUs or memory.
Yeah.
And how do you educate those? So that's where I was coming from.
Yeah, that's an amazing conversation, which we can continue after. We have more questions.
So this hopefully will be pretty short. It might be a dumb question too, but I think Jack touched on it a little bit. Tobias Mann with the Register, by the way. Every time there's a new top 500, I'm looking at peak performance, theoretical, versus what was realized in HPL, HPG, and I'm always curious at what point we are running up, particularly with HPL, we're running up against the interconnect as a bottleneck. And it really feels that at 200 gigabit, we're really seeing that on the larger exascale machines. And I wonder if you could talk a little bit about how big an impact that makes in the real world, as Jack alluded to with HPCG.
So it's all about data movement. It's not about floating point operations. So the machines are over-provisioned for floating point, and we have really the bottleneck is around moving data around in the machine. And if you increase the bandwidth associated with the hardware, you'll see an improvement in the overall performance of the applications. That's an easy way to get that. Of course, it's hard to get an increase in the bandwidth. So we should be looking at ways to do that. Optical comes to mind, but there are many ways, I think, to get at that.
Okay, one question for you, Jack. Since you were the one who enabled matrix multiplies to kind of catch on, how come life provides so many matrix multiplies?
Well, as I always say, it's all about linear algebra, and it's linear algebra all the way down. So matrix multiply is a fundamental part of that equation.
It's like it's all your fault, Jack.
Thank you. Just to touch on what you were answering just before, why matrix multiply is a key part of life. In terms of architectural development, and I also apply this to Microsoft, are you seeing things that give you hope that supercomputers will speed up? The AI community is doing a great job scaling because of these huge models, but a lot of the hardware is common, but it's a different problem set. But are you seeing any developments in technology that give you hope that it's not just going to become a flat line and each year you're showing this projection, but you're starting to see some ramp up? Any thoughts?
Well, I'm concerned that the future for high-performance computing will be not doing 64-bit floating point arithmetic, right, not 32-bit floating point arithmetic, not even 16-bit, but 8-bit and 4-bit, because that's where follow the money. That's where the money is. So that's a concern I think we as a HPC community should share. And I would like to keep higher precision arithmetic around a little bit longer, so we could actually solve the problems that we want to at the right fidelity and the right levels. So that's my concern at the moment, is that if you take a look at the newest Blackwell NVIDIA chip, you'll see that the performance for double precision has actually gone down. So it's not going up with the new product; it's going down, and that's a result of of real estate being given to some of the other parts of the architecture that are considered more important at this moment.
So does anything give you hope?
I always have hope. So there's great algorithm innovation taking place to tap into the integer and low precision floating point that might, in fact, give us the benefit of that hardware at the higher, building up to getting higher accuracy. So again, algorithmic improvements are important. We need to go through it. We'll be forced into that position because of the hardware not giving us what we need.
Yeah, I'll just build on exactly what Jack was saying. Like, I do think as physicists have more access to int 8, int 4, FP4, like lower and lower precision, they'll figure out algorithmically how they can use that to still achieve some degree of fidelity. I do also wonder at some point if there will be an inflection point where even in the AI community we start to see that what we have lost with the higher precision was something that was meaningfully lost, because we are going down this path of actually removing silicon that does 64-bit precision. And I do expect that at some point the inflection point will turn the tide to where we'll start to appreciate the extra bit of fidelity that came with precision. So, yeah.
Okay, one more question.
So my question goes back to Helena. So in your talk, you talked about the bad, and you talked about, the focus has been on QPU hardware development and the lack of emphasis on the algorithmic development. But isn't it true that the reason that there's a lack of algorithmic development is because of the fact that there's a very difficult challenge of overcoming the high quality, high performing qubit challenge because of the error, and as a result of that, it's difficult to scale, get those deeper, wider circuits that you need to be able to map your algorithms to. And if you can't map your algorithms to the circuits and the circuits can't map to the hardware, then you have an issue. So I was wondering why you saw that as bad as opposed to another step that needs to be solved.
Well, the bad is in terms that we are focusing mostly on the QPU right now. We have a great tool available as in the simulators, right? They are doing the job. So what we can do, and frankly, with having about 50 qubits, you can do, a little bit of training. You can do a few exercises, so you can start adapting and developing the software part. Right, and we are doing that right now already. We have been doing it for, I want to say 5 years, seriously, right? And the issue is when you do have the fault-tolerant qubits later on in, let's say, next year or the year after, which we expect, you would want to start actually with the meaningful calculations. So at that point, you would need to have solved some of the additional problems that I mentioned on the other levels, right? So you have the speed up. So the problem is, and I think this is also a bit of this hype situation, the problem is the expectation. What we have in the market right now with all the hype from media, with all the hype from the governments which are sponsoring this development, is that we do have some meaningful results at some point. So now we are expecting this 1,000 qubit kind of threshold, right? Which everybody was waiting for. And now that you mentioned, for example, the IBM, who have announced that this will be available, right? And it is available already. So now the expectation is that we are able to actually use that stuff. And we are not necessarily at that point yet. So for me, it's a bit of a bad thing, potentially, because for me, it kind of correlates to the AI development, let's say 10 years back, when we kind of had this expectation, then slumped back in the AI wintry area. And I'm a bit afraid that can happen to quantum as well. So for me, that is why I see it as a potentially bad development, which we need to address.
Well, great. Everyone, let's thank our panelists one more time. And they'll be around if you want to ask questions. I'm sure you'll be able to find them. And thank you for coming.